welcome back. And about 2 years ago, oh man, it's been a long time now that I'm thinking about it. But anyways, a long time ago in a galaxy far, far away, I built up a little 1-bit computer on the breadboard. And it was based around the Motorola MC14500, which is a little 1-bit industrial control unit that was meant to replace relay ladder logic in industrial applications. And the design of the computer was not actually a unique or original design. It was just a recreation of the minimal ICU system outlined by Motorola in the MC14500 handbook. But because breadboards are kind of a transient thing and they're meant for prototyping, that 1-bit computer that I built was very quickly taken back apart and the breadboard was used for other things. And I've been kind of lamenting the fact that I don't have that anymore. So what we're gonna do is we're gonna build that minimal ICU system back up again, but we're not gonna build it up on a breadboard. This time we're gonna build it up on a PCB. And what better way to do that than to give my friends over at PCBWay a call, who were gracious enough to sponsor this episode. Now, before you skip ahead 30 seconds, a lot of YouTubers will do a sponsored segment and they'll just show some B-roll and go, yeah, go visit them, they're great. Well, I'm not gonna do that because I'm gonna show you the actual product. This is the PCB that I designed and that they sent me. And there's some interesting things that we can check here. Because I'm not great at designing PCBs, but also I like things to be very visual, and this is kind of an art project already, I made some interesting design choices here that are gonna really let us kind of peel back and look at the under layers of how PCBWay makes their PCBs. Most notably, you can see that there's no solder mask and no silkscreen. It's just exposed fiberglass board here with exposed traces that do have hot air solder leveling on them. Also, the traces are fat. I use 1mm trace widths, which are huge. They're like twice as big or maybe even more than the standard trace width. And also the trace width separation is massive. There's a 2.54mm separation between each trace, which is like the standard dual inline package separation. Now, what that means is that we can, from pretty much any distance, clearly see what traces are going where. And we can also do another test. This was actually unplanned. I made an error in the PCB design here. Right here, there was just an errant trace that I forgot to delete on the original design file. And so this would cause a problem. So I need to cut that trace. But because it's just kind of hanging out here in the middle, I think I'm gonna try and lift the trace and we can take a look at how strong the glue is that is used to hold the copper to the fiberglass. So that's gonna be a fun test that we're gonna do a little later. And then, well, we're gonna populate this with all 14 of the ICs. This is a huge board for just 14 ICs, but we're gonna populate it with all of the ICs that are on there, and then we're gonna put some power into it and give it a test. I have absolutely no idea if this will work, if my PCB design is correct or not. That's something that we're gonna figure out together. So let's hop over to the bench, take a look at the PCB, solder it up, and then we'll give it a test. So let's get started. It's not often that you get to see a PCB without a solder mask on it these days. I think it was a bit more common back in the day. I have a couple of Centurion PCBs that don't have the solder mask on them, but most notably on this one, you can see that whoever the manufacturer was that supplied the copper-clad PCB stock to PCBWay is KB here. We can see that their logo is in the actual fiberglass. But interestingly, it's only on one side. If I flip it over to the back side here, there are no logos at all. It's just a nice, beautiful, smooth fiberglass going on. Unfortunately, the logo ended up being on the front side. So this is the side that's going to have all of our LEDs and our switches, and KB is going to be a bunch of visible places. I can't imagine that PCBWay would have any indication to know which side of the fiberglass KB is going to be on. It just so happens that for me it was on the top side, but on the next batch of PCBs that I order without a solder mask, it could very well be on the other side. I mean, it's just a dual-sided copper-clad PCB. It just depends on which way they set it down. Now, I mentioned on the back side here that I do have a design problem, and that is right here. You can see that there's just an errant trace that connects these two traces to each other and then goes off into oblivion. But I'm curious if I can actually peel this up, peel it off, and see how strong the glue is. So I'm going to grab an X-Acto blade and let's give that a shot. I'm just going to try and get right under the edge here, see if I can peel this up. So after picking at this for a little bit, it looks like I can kind of cut off the top layer of hazel, but getting the actual copper off the FRP is proving a lot more difficult. Getting a lifted trace on this is going to require a lot of heat and a lot more effort, I think. I think what I'm going to do is I'm just going to slice it right through here to break the connection, and I'm just going to let Mr. T here hang out as Mr. T, and hopefully he doesn't pity me, the fool, too much. But I am really impressed with the PCB. I think it turned out absolutely beautiful, and not having a solder mask I think is going to make it look excellent once we get it fully populated with all of the ICs and LEDs. So I think it's time to break out the soldering gun and start putting components on here. There's only 14 ICs, but there's like 25 or 30 LEDs, so there's a lot of LEDs to solder up and not that many sockets, but I think it's going to look brilliant when we're finished. And here is the finished product, and it looks absolutely brilliant. I could not be happier with the way this turned out. It's just, it's a piece of artwork. It's something that I would like to hang on the wall or prop up somewhere and have it be on display. But all the art that I build, I like to build it as kinetic artwork. So it has to move, it has to operate in some way. So let's go ahead and flip the power on here. The clock is halted, so I will resume it. And yeah, there we go. We can see it building values up into the scratch register and the output register up here. And then it clears those values out. It's doing exactly what I programmed it to do. So my piece of kinetic artwork is actually functioning perfectly. But it took a lot of effort to get it there. It's been about 2 days since I last turned the camera on, and most of that was spent troubleshooting. There's a couple of bodges going on here on the back, and there's just a lot of boneheaded mistakes that I made. So I'll tell you what, let's zoom in on these and let me show you everything that I got wrong. First things first, what exactly is it that I've built here? Well, I've got the schematics for it here, and this is the clock and program counter. The clock is generated out of two 555s. I can either have the clock be an astable multivibrator or a monostable multivibrator, so I can single step through. That clock goes into a 74HC double aught over here that is essentially a flip-flop that allows me to halt or resume it. And then that goes into two 74HC 163s that generate an 8-bit address that we're going to feed into our ROM. And if we look at the next schematic here, our ROM is an AT28C64, which is massive overkill, but it takes the 8-bit address in and gives us an 8-bit instruction value out. Now I did add a little extra switch here so I could switch between two programs, which of course means that we only have an 8-bit address coming in, which means we only have a maximum of 256 instructions. So we have to be pretty smart with our programming in order to get anything useful to happen. Now you'll notice over here on the right there's a little inverter chain going on. This was a bad idea. The goal of this was to allow the ROM to stabilize before the processor actually executed any code, but this just caused problems and turned out to be totally not necessary. And then on the last page of the schematics here, we've got the complex part of it. Up here in the top left is our actual MC14500 4500 that's doing the hard work. And then we have essentially an input register, an output register, and a scratch register. So the input register can only be read from, the output register can only be written to, but the scratch register can be both. You can write to the scratch register and then read that value back out again later. So it's a really simple system. Now looking at the schematics here is maybe a little confusing. So if we look at the actual minimal ICU system here, that might give us a little bit of a better idea of what's going on. We've got two 4-bit counters giving an 8-bit address into a ROM. The 8-bit address goes into the rest of the system. Now the MC14500 uses 4 bits as an instruction, and that leaves us just 4 bits for addressing and selecting input, output, or the scratch register. 1 bit is a chip select. When that bit is 1, we're either reading from the inputs or writing to the outputs. And depending on which one we're doing is dependent on whether the write signal coming out of the MC14500 is active. Now, if chip select is 0, we're working on the scratch register. And the scratch register is a little more complex because we can write to it or read from it. And that is, again, dependent on whether the write signal is active or inactive. And that's the whole system. We have 1 byte of RAM, external input, external output, and a little tiny 1-bit processor. So what did I get wrong on the actual PCB here? Well, first thing, I just completely forgot to connect up the ground pin of all of these 16 LEDs up top, so they didn't illuminate right off the bat. Also, I have the power and ground lines going vertically underneath all of the ICs here, and I tied them all together both on the top half of the board and the bottom half of the board, but I forgot to tie the top half of this row and this row together. The 555 timers that I'm using for my clock circuit over here, I totally forgot to put decoupling caps on those, and that was causing double clock pulses to show up. So I just soldered in a little extra decoupling cap across one of them here, and that fixed that problem. But then I had more program clock problems. I was running the clock through an inverter chain to create a delay, and the values weren't latching correctly, but if I removed that chip and just bypassed it completely so the delay line wasn't there, it actually started working again. But in order to keep the board looking pretty, I left it in, and then I put just a little capacitor on the actual delayed clock line that's coming out of it, and that totally fixed the problem. Also, finally, I had a marginal MC14500 in there. Fortunately, I have about 3 of these, so I popped that out, put a new one in, and boom, the whole thing came alive. Now, there's a couple other interesting mistakes that I made. All of the input switches here are backwards, first of all. So down is on and up is off. Also, I put a little header over here for an external input, but I didn't wire it up correctly. I should have put pull downs to ground so an external input could have pulled the value high, but instead it's just directly connected to ground or directly connected to 5 volts. I'll fix that on Rev 2 of the PCB design. So that was the major problems. To give a quick outline of what it is that you're looking at here, on the bottom left here are our input switches with an external input header that's totally useless. We've got our dual 555s down here that is adjustable in speed or through single stepping through this little toggle switch right here. Our scratch register is displayed on these yellow LEDs right above it. The green LED here is just showing our clock. Here, the yellow LED is our result register. The 4 LEDs here are going to be flag O, flag F, jump, and return, I think. Those are the 4 flags that the MC14500 can output, and they have their own external header right here. We've got 3 push buttons right here. This is halt, resume, and reset. Up here next to the ROM, we've got a toggle switch to switch between our 2 stored programs. Then these green LEDs up here on the top left are the output register, and we have an external header for those as well. Right above that is the 9-volt power supply that's going through a 7805 to put power into everything. And then up here we've got our 8-bit program counter that's coming in here, and then our 4-bit instruction, our 1-bit chip select, and our 3-bit address. So this is going to be the 8 bits of data that's coming out of our ROM and controlling the entire system. And so we'll flip the power switch on here. The system is currently halted, so we can resume it by pressing the black button here, And we should see the scratch register fill up, the output register fill up, then the scratch register disappear, and the output register disappear. And yeah, it seems to be doing that perfectly. So what exactly is this program doing? And so I've actually got that outlined right here. This is just a simple test program to test some of the functionality of the machine. So let's flip it over to single step here. We will reset the machine. All right, so we're sitting at the first address here of 00. This is just a NOP-O. Absolutely nothing happens. So the first real operation that we run is a 0110 at chip select 1 address of 000. This is an OR complement. It forces a 1 into the result register, and we can see that that succeeded because our result register here is currently on. And so we now have a 1 stored in the result register, which means we can use that for the next operation, which is a 1010. Chip select is 1, address is 000. So we're putting the result register on the data bus. So the data bus is currently at 1, which means we're storing that in the input enable register, allowing inputs to come into the MC14500. And the next operation is a 1011. Same thing, but now we're doing it for the output enable register, meaning outputs can now leave out of the MC14500. That initializes the processor. The system is now ready for use. The next operation is just another NOP-O. Then we go to a 1001. This is a store complement. It stores the inverse of the result register into scratch register address 000. And well, the inverse of 1 is 0, so that looks like it worked correctly. The next operation on here is a NOP-O. The operation after that is actually a load. It's a 0001 operation. Our chip select is 1, and we're loading from address 001, which is going to be our toggle switches down here. And our toggle switches are down, which means that they're set to on. So we load a 1 into the result register. The result register kicked on. That is correct. The next operation after that is a 1000. This is a store. We're storing it to, well, chip select is off, so we're storing it to the scratch register, and we're storing it to address 001, which kicked on, and that is working perfectly. So that's exactly what we wanted it to do. And then this just repeats for a bunch of subsequent operations to fill up the scratch register. And when we get done filling up the scratch register, we do essentially the same thing, only without the loads. We just store whatever is currently in the result register into all of the output register up here. And actually, single stepping is really only useful for doing very slow single steps on this. It's supposed to just be run with the clock on. And so if we flip the clock on, we can see that the scratch register builds up, the output register builds up, the output register empties like it's supposed to, and then the scratch register empties like it's supposed to. So it looks like everything is working perfectly, but well, I mean, this is kind of neat. We've got a lot of great blinking lights, but how useful is this thing? You've only got 1 byte of RAM and you've only got 256 instructions. There's not a whole lot you can do with that, right? Well, turns out you can actually play a game. So what we need to do first is, I'll go ahead and halt it here. I'm going to turn all of my input switches off here. And then we'll flip over to our second program. I will reset the machine. Gotta resume it. And then if we let the reset off here, I'll speed it up just a touch here, make it run a little bit faster. You may notice that we have a single bit moving left to right on both the output and the scratch register here. Now I'm looking at the output and I want to maybe kill that bit. So I'm going to toggle a switch here at the right timing to hopefully turn that bit off. I missed. Now I've got 2 bits circling around. All right, let's try again here. I got 1. Yeah. If I get it at the wrong timing, oh great, now I've got 3 bits going on. But I got 1 of them, so I'm back down to 2 bits. This is an actual game. This is probably one of the oldest games. It's called Kill the Bit. It's unbelievable. You can play an actual game on this machine. Now, I didn't actually write this program. It was written by a friend of mine and a member of the Discord, Yaros. He's an unbelievably good programmer, and he's really good with these kind of strange esoteric systems. He wrote Kill the Bit, and this is the actual code for it. It's kind of split up into sections. We've got a basic setup here that preserves the result register and then enables inputs and restores the result register. And then we have a little bit below that that runs only once on startup, and this is just initializing the memory with a single bit. And then we get into our main loop, and we're displaying all of the bits, and then we're doing an exclusive OR of whichever bit it is that we're working on with the input here. And you can do an exclusive OR by doing an exclusive NOR operation and then storing the complement of that. And so that is how we're determining whether I'm hitting the switch at the right timing. And then we do a lot of looping of that. And then we get down to the next bit, which is even more looping of just rotating the data. So all of this load store that's just going continuously for several iterations is all just to loop the data. And then finally, we put a 1 into the result register with a OR complement so that we can skip that initialization that adds a bit into there. And this is just a brilliant way to write this. Now, Yaros is not mad like I am, and he actually wrote it in a much more sane way by creating a script that runs correctly. And this is actually his particular code that he compiles into raw binary that I then copied over to the ROM. And well, you can see it pretty much just outlines exactly what I was showing, only whenever it comes time to do something where we've got to repeat something 7 times, he just does a dot repeat, puts the code that needs to be repeated in there, and then a dot end repeat. And the compiler just figures it all out, dumps it into raw binary. This is a much more sane way of programming for this machine. But yeah, there we go. We've got Kill the Bit written in pure MC14500 assembly. That's a really cool. Yaros, you knocked it out of the park. This is amazing. I'm going to put links in the description below to pretty much everything. There'll be the full schematics. There'll be the Gerbers for this PCB. Well, not this PCB exactly. I'll put an updated Gerber that fixes all the dumb mistakes that I made on the back. There'll also be a link to Yaros's code. And Yaros, I said this earlier, but absolutely stunning work. When I first started this project, I didn't think it was possible for the minimal ICU system to play one of the most iconic games in gaming history, but here we are, Kill the Bit, chugging away perfectly on our minimal ICU system here, and it wouldn't have been possible without your help. So Yaros, thank you so much. This is stunning. It's so cool. This is so cool. But if you as a viewer want to rebuild this system, everything is down there in the links for you to be able to do so, although I wouldn't necessarily recommend rebuilding it exactly like this. This is a horribly inefficient PCB design. You could shrink this considerably. I put these huge buses on the right side that you can't even see from the top. That's totally unnecessary. You could eliminate those completely. And if you shrink the trace widths down to a more sane size, I'm using an extremely fat 1 millimeters here, but if you bring them down to a more sane size, they'll fit in between the pins on dip sockets, and that allows you to really make the PCB layout much more compact. You could probably bring this entire layout down to something that fits in the palm of your hand, probably about 1/4 of the size, and that would be epic. That would be really cool. And if you do build up one of those, send me a message. I would absolutely love to see it. So I want to give another shout out to PCBWay for hooking me up with this massive PCB here. So I want to thank you guys so much for joining me on the journey of getting my 1-bit minimal ICU system back. I am really happy with how this turned out, and I think it's going to look great sitting here in the room. So thank you so much, and I hope to see you in the next episode.